Good afternoon to all. Welcome back. During the lunch break, we talked about examples, testing, how do you find out what is available in ParaView, etc. And I said, hey, if you compile your own VTK or your own ParaView, with ctest, you actually have a list of all the tests implemented in the code. Here is a very short example of if I ask ctest to give me the names of the filters available for SPH, related to SPH, I get 2 CXX or C++ tests, and I got 3 Python examples. So I can simply run those examples by indices or by text, and then the Python code is very easy to explore, so I'll go look in there to see how it's implemented. Now, doing this on an empty keyword brings me 2,678 tests, so there's quite a bit of material there. This morning, I've already done some early approach to parallel visualization by simply flipping on and off the enable auto MPI flag in ParaView. I think even with the precompiled ParaView, it should work on most Linux distribution. With Mac people, have you made the experience? Does it work as well? Okay, so that's pretty good. Where you can take advantage of the local CPU resources of your desktop. Now, however, we here at CSCS, the real thing is really to do client-server with the CSCS installation of ParaView on Piz Daint, because we have large memory nodes, we have very powerful GPU, and we have access directly to the Scratch file system. So this is what I'd like to demonstrate. And perhaps before the coffee break, we could try it with some of your accounts, okay? Because as always, doing those client-server connection can steal a lot of time from our afternoon. We'll have to see. Basically, I'm going to present the interface to you. At least you will be familiar with how it should work. On my local desktop, I have a number of hosts, different supercomputer systems. And for your purpose, if I use Daint, we're going to use the so-called reverse connection approach of ParaView. What does it mean? It means that the GUI, the client on my desktop, will open an SSH connection to Daint, to the logging node, submit a job request. When that job is allocated, the ParaView server runs on the compute node and connects back to my client. So the client actually waits until the job is enabled. Okay? This is how the interface looks like. It gives me the choice for the number of nodes I want to use, the number of servers per node. So when I talk about a node, I talk about one hardware unit on Piz Daint, which is made of 1 CPU, 12 core on the hybrid partition, and 1 GPU, which is the NVIDIA Pascal GPU. And then important is a user ID, a port number, and what you're supposed to do here is use your own private user ID to connect to the machine. You select how much time you want to run, and then the job gets allocated and sent back to you. Now I'm going to do something very simple such that I can run very quickly. and I want to show you the output of it there. Once you start an allocation on Piz Daint, this is what you should have on your screen. It should show you the details of the S-batch submission. So here, 4 tasks, a single node. It loads the ParaView module and then some additional modules. In our case, we now use the ClientPython module. So this is all those details are included in the shell script I give you, so you don't have to type any of this. And then once you're connected, this window pops up. It means here I'm connected. So you see the wait time was just a few seconds. And it gives you a list of plugins. This is interesting now because for some plugins to operate, you need to have the plugin loaded on both sides of your connection, the client and the server side. So here I have, for example, the different plugins for the data interfaces I have done for customers. So here the ETH Zurich Geophysics department, here the ETH Zurich Biomedical department, here the Tipsy people for University of Zurich, and so forth and so on. And you see on the other side the same plugins again. Here, by the way, is the NVIDIA index plugin, which we could load if we wanted to exercise that particular feature for the moment. But for the moment, we'll just bypass that. Okay, am I really connected here? That's the question. And what resources are available, actually? You're supposed to check that with the help menu. You'd go to help about, and it's going to pop up a menu with 2 sides. It has the client information, and it shows you the version of ParaView you're using, the Python version you're using, the NumPy, Matplotlib, etc. It shows you the GPU you are using. This is important to make sure that you are actually loading the correct OpenGL library both on your laptop and on the remote side. So here it's showing that I have an NVIDIA GeForce card. This is a mobile device on my laptop, and it uses driver 384. That's the version of the OpenGL driver. On the remote side, which is the connection information, it says, yes, I am doing a remote connection. That's the important point. Number of processes is 4. That's exactly what I asked for, so I'm good. It shows that I'm using the ClientPython module, and at the bottom it shows 2 interesting things: the Tesla GPU, the name of the driver, and it shows that I'm using EGL. Somebody during the lunch break was asking me about X server. We're not using X servers anymore on the Piz Daint side. We're using the so-called embedded GL, which is X serverless OpenGL accelerated on the GPU. So this is a good indication already. The last trick I have to test my remote connection, as you know, is the standard wavelet example, which you create, and then you visualize the process ID. And here, sure enough, I have 4 different colors, which is a guarantee that you're using. It's a guarantee of 2 things: that you are using 4 ParaView servers, and it's most important, the guarantee that you are using distributed, equally distributed sub-partitions of your domain. I'm good with that. And by the way, as I move the mouse around, do you see that the edges are pretty fuzzy? And then when I let the mouse go, they render very nicely. let's go to settings, render view, and I'm going to show you some tricks, more tricks. I'm going to set that to 8. What is happening here? Because I'm interacting with the remote server. Suppose you are perhaps at home, where you don't have super high-speed telephone and wireless service. You'd like Piz Daint to send you a very small image during interaction, so you don't waste your bandwidth. And then when you let the mouse go, it sends you the full image. That's exactly what this is happening here. Here, I'm interacting. I send a reduced resolution image, and then when I let go, Piz Daint sends me the full image. So I've saved on bandwidth. This is, by the way, demonstrating that the server is sending me an image and not a geometric object. I can turn that off. There's a threshold because this object is pretty small. If I go back to my settings, over here, settings, render view. My settings is set to 0 because I usually like here. No, that's not this. Remote render threshold. If I set that to a large number, this is in terms of megabyte. Here now, everything is smooth, even though I'm interacting with the model. What does that mean? It means that the server has sent me a copy of the geometric object, which is now owned locally by my own GPU, and I can render that very lightly. All right? There, I'm good to go. So the details about this is ParaView client server. You have copy of all those nodes, okay? No problem with that. I just need to assemble. Unfortunately, I didn't have time to finish that. Assemble those different parapoints together. Doing a client-server connection is much faster than using a VNC desktop, for example, or using SSH-X. You should not do that. And in fact, if you were to do SSH-X to Piz Daint, you will not find the ParaView client. This is done on purpose. I've removed it from the compilation. It's to oblige people to use the client server, but it's for your own benefit. Okay? So we need to configure a few things. Here are the details. Windows user, it's a bit more complicated, but this is all very well documented, and I can send you the PDF of all this if you want to set that up. You need to use Putty, set up a private SSH key, and you need to create a Putty Session on your laptop. For all of us, actually, Unix, Mac, Windows user, you need your user ID. So the examples I'm given here are using 1100. That's my user ID. You should replace that with yours everywhere in the slides. Create a Putty session. Call it whatever, but if you use the standard name, that's less work for you to configure. Okay? And we need to give a fixed IP address for Daint, so we specify Daint 101 or 102 or 103, one of the logging nodes of Daint. But that has to be a fixed name. You set auto login username with your own username, I hope. In the connection proxy, you set that particular command, plink, your username at ela.ch, that's the entry point to Daint. Exactly this, you have to just type it exactly as it is. I'll send you the PDF file. And then we need to set up a so-called reverse SSH tunnel. And the configuration for this is to use localhost, the name of the destination, and then your username. What is this SSH business? It's about creating a tunnel to the compute node such that the compute node thinks that it's connected to something called localhost. And in fact, because of the tunnel, localhost becomes your client. It's all automatic. It all works out of the box. We've spent quite a bit of time developing this, and it's pretty good. It's well tested. On the client side, you'll have a couple of files to copy. So for this particular workshop on Piz Daint, I have created this file here, which you can copy to your desktop, change the username with the username we've given you in the list this morning. And then after the workshop, once you go into regular production usage, you can use those particular files. This is also documented on the website of CSCS in the official documentation. So those files contain the server initialization routines you need. Yeah, in the PVSC file, you change the user ID with your own user ID, for example, 1234 here. And we use the user ID to set up the SSH port. This way it becomes unique. This is the reason for using your user ID. It's unique among all users that do access to Piz Daint. In the connect load server GUI, you load that particular configuration script, and then you have it become part of your, and this is something you only need to do once, this loading of the configuration, then it comes back every time you start ParaView again. And this would be the standard menu we've seen already. Make sure to use your username, your private copy of the shell script, and then you can select different things here. For the moment, we have the GNU 5.4 version installed. I have it already written as future version 5.5. I think in a couple of weeks at the most, I will switch back. I will switch to 5.5. A Windows user, you don't have the command /bin/ssh. You have the command called plink, which is the same. Make sure you have the full address of plink here. Make sure, because of those spaces, which Windows recognizes as spaces, make sure they are enclosed into double quotes. So you really should have double quotes here for the full name, C program files putty plink.exe. And then if you have problem with that, you send a mail to the help desk, and I will respond to those emails. And this would be the standard console output as we've seen in the examples earlier. So for this course, we have a reservation called this course. We'll see if some of you can manage to use it. That's what it is. And how do you really check you're connecting? This is what I showed earlier with this particular image. Okay? So that's the thing I wanted to show. The next thing I want to show is importing ParaView extras.
Will you try the connection now?
Perhaps we could try before the coffee break. This way I make sure I do at least this material. And then once you connect it, then you can try all those different things at the same time. Right? ParaView extras. What is this particular thing I've prepared? there are many file readers, but perhaps you still have data that doesn't correspond to any of those file formats. So adding your own reader would be one option. And you could do that via a plugin. So doing a custom plugin is one way to customize ParaView. Another option is to use VTK algorithms which are not actually visible in the ParaView package. And then I'll have some examples on how to do this. ParaView is an end user application. So it's basically VTK wrapped up with a GUI. But there are so many classes, so many options, that they've limited that to a certain number of commonly used filters and algorithms and so forth. So if there's something you know that exists in VTK but is not exposed, you can actually, in many cases, you can import it in ParaView. This is how you would do it. You would look through the VTK examples, okay, looking through the testing suite, etc. We've seen today, this morning, the use of the Python programmable filter and sources. This is most often the place where you would import that functionality. We'll see about that. We can also import that through XML code, or via the plugin manager loading new plugins. Here's one, pretty useless, but it's an example that has existed in VTK for a long time, the so-called platonic solid. There's the option between creating a single tetrahedra on the screen, a cube, an octahedron, an icosahedron, etc. Well, do you have this module available? No, it's not there. Like I said, it's useless. It's something that was developed 15 years ago, but it's a great example for how would you do it. You would do it exactly with this. This is the XML code you would import into ParaView. So we have to understand the syntax of this XML code. Now, for the glue around it, the best thing to do is to look at the already existing examples. So on the website, or if you compile from source, there are 3 files I look at all the times called readers.xml, filters.xml, and the last one is probably representations.xml that I looked at. And then I just take examples, I copy and paste into my own, and then I change the class name. And then I have to find out about the sliders, the buttons, etc. So the best thing to do is look at an existing filter or source. Say, oh, I want my interface to the class to be exactly like this other filter that's already implemented. You go look at the XML code, and you find how it's done. It's really nothing magic. So in this case, I want to have here a little menu where I can flip between those 5 different values, and the XML code is basically an enumeration domain with the different values, the different tags associated, and then you have to find the command, the class in your class object, the command that will respond to those different numerical values. So you look on the website for the class name in the class hierarchy. You will find that the class called VTK Platonic Solid Source has one method called setSolidType. It takes a single element, default value 0. It's an integer, so integer vector property. That's it. That's the XML code. So if I do it here in my own ParaView. I forgot. I go to Manage Plugins. Good. Load New. I'm going to look for XML code. Home. I forgot where I put those. Projects. ParaView somewhere. I don't find it. ParaView. I have a little problem here. Was it difficult? It was exactly where I thought it was. So ParaView, I will restart ParaView. Manage plugins, load new, import XML code. There it is. Platonic XML, OK. It's loaded. In the source, I now have a new menu called Platonic Solid. Okay, and I have a selection here. The 5 different choices I had mentioned, and if I select tetrahedra, there's a nice little tetrahedra on the screen. Okay, very exciting. Good. Next slide. Here's how you do it. You find a class name. Go to the class hierarchy. This is the C++ class, virtual void set solid type, takes an integer, specifies this is the documentation written. You look in the ParaViews readers of filters.xml, which are right here at this address. You look for something similar, and you copy and paste the code. Second example, graph layout. In my VTK build directory, I found this really nice algorithm called graph layout. It usually takes an unbalanced tree of objects, so edges and vertices, and it balances it. We're going to see the demonstration of it. That's basically it. Here you see a graph, edges and vertices. It's not equally, I mean, the edges don't have a specific weight in that case. So it would be nice to have this particular type of display, for example, where things are a lot more balanced in space. So it's the graph layout example in my code. Sorry. So if I go back to my ParaView here, I will simply show you the code. Graph layout. In this case, it's a filter, so it's in the category called filters. I call it graph layout. The class name, that's the original class name. I shouldn't change that. VTK graph layout filter. And this gets a little bit more involved here. Now, because in the case of sources, we didn't have to specify a type. Here, it's a filter, so it sits in the middle of your pipeline. We need to tell ParaView which type of input is enabled for that particular filter. And the type is VTK polydata. And also, if you don't know that, this in the class hierarchy documentation, you would find exactly this. This input is designed to work with VTK polydata. So this is what you specify here as an input type. This property specifies the input data set for the graph layout filter. And then it has one parameter, which is an iteration value. The class hierarchy tells me that the command is called set max number of iteration, and I give it a default value of 100. That's an integer also in the code. Then it has one double value called the cooldown rate. It has another flag here called to switch between 2 and 3D space. In this case, it's a Boolean. So this would be 0, 1. We're good with that. And it has a final input called automatic bound computation, again a Boolean. And this will be the code to import to enable this particular filter into your ParaView. Last example I have is with molecules. There was this blog article already a couple of years ago, I think, introducing support for native object. There's a class actually called VTK molecule in VTK, but it's still don't see it very often used in ParaView at this point. Some data formats, such as PDB, for example, the protein data bank format, include both the types and coordinates of the atoms, but also the links between atoms. Okay, for example, the water molecule H2O, two atoms of hydrogen, one atom of oxygen, and they are connected to each other via bonds. Well, if you don't have bonds, there is I'm not talking about James Bond, I'm talking about bonds between atoms. If you don't have bonds in your input data set, VTK knows how to calculate that, but that feature is not included in ParaView. It's a class called VTK Simple Bond Perceiver. So for that particular case, I implemented it via the programmable source, via a programmable filter. And we have an illustration of it here of a molecule represented with all its bonding. So this I thought could be an exercise. Implement this simple bond perceiver as XML code. If I go back to how you do it, where's the magic? You would have to find the VTK class name in the hierarchy, find the attributes you wish to expose. You don't necessarily have to expose in the GUI all the attributes that the class knows as implemented. If you want a single or a few of those attributes, you select just a few of those attributes. For those particular attributes, look exactly for the name of the command, the C++ command, implementing this setting of the attribute. Look through examples in the ParaView XML files and then derive the code. Now I realize, because of the time, It's probably quite a lot already to do. So I'm going to show you this as a second example, and perhaps you can try to redo it with, in all tranquility next week or so. Interesting, I see the word time step here. We haven't talked about time step, about time-dependent data yet. So I will make a parenthesis to do this. This actually is quite an involved exercise because it makes you create the XML code, load this particular data, then discover how many time steps are available, and then find out how to animate that through a batch computation. And this is another thing missing in ParaView that I wish to explain to you. Let's look at the example on my desktop here.
Do you mind if I interrupt you for a second?
Yes, please.
You mentioned about the time thing.
Yes.
How can we synchronize time in ParaView? Because I've encountered sometimes issue because there is this animation time, there is this timekeeper time, and sometimes in a Python script when you update this timekeeper time, it is not always passed correctly to the readers. How do you synchronize time in the pipeline?
I'll try to answer this. So let's look at the code for the molecule bound. The class is called the simple bound perceiver. It takes as input a VTK molecule this time. It has a parameter called the tolerance, and the command is called set tolerance. The default value is 0.5. Now I need to find the data set. I have data set all over my desk, here. XYZ. It's an external data. There's my molecule. It's gold, only atoms of gold. There's no bonding. So, tools, manage plugins, molecule bound, I'm going to activate that. And now in my filters, I have this compute molecule bound available. I apply it, and sure enough, I now have the bondings between all my atoms. There was one question about time step. How many time steps does this data set have? Interesting. It shows it has none, but I know it has 10, because see, I can animate through it. Okay, so I picked the wrong example. I wanted to show you that in this information tab, normally you have the time steps, the list of time steps available. Possibly for VTK molecule, that hasn't been implemented yet. This had escaped my attention. So let's go to the Python command. Remember, my active object is what I want to get to, so I'm going to say reader equals get active source. I'm going to get help on my reader to see what's there. Or I can simply say reader dot list properties, for example. And this is really interesting. It doesn't show the time step. Okay. Pardon me? Yes, it is. So I think it must be a GUI undocumented feature. So there is my molecule and animation through the molecule. Now, back to my Python view. View equals get, or v equals get render view. This is going to give me all the attributes about the rendering view. And as you can see, there are quite a bit of options available. One of them is view time. So I could simply say view time, and it shows 9. And if I reset, if I go back to time 0 using the arrows here on the top and look at my view time again, I get 0. So that's correct. So this is really telling me that the view, which is the bottom of my pipeline, drives the execution. Here I am at time step 0. Okay. If I simply set view times equals 9, and if I render, there, I flipped right away to time step 9. What bothers me is that normally the source object should have a list of time steps available already, and I don't see it. So that's kind of bothering me a little bit. But let's take actually advantage of this to look at a special mode called the comparative view inspector. Which seems to be not active, probably for the same reason. Never mind. Bad example. It's a bad example. Save. There's something else I want to teach you. I'm going to clear this, delete. If you want to learn the Python code step by step, there's also a way to do this. Let's take an example. My wavelet cube here is here. I'd like to see what happens when I create an isosurface. So if I go to the Tools menu and go to the Trace feature, and I show Incremental Trace, like this, when I click on isosurface, it prints to you in this window exactly the Python code that is being created for the pipeline. So in this case, contour, the input is the wavelet, and the threshold is the default value. And then as you say, apply, I don't see where my window went, but I'm going to say stop trace. And it added to it the show command, which we've seen already, and some of the default attributes. So by doing this, you can actually follow step by step what you're doing. To make sure I have a good-looking time-dependent data set, and I can finally answer your question about time, I'm going to load this particular script, which I will give to you at the end, called time step, called transient point, ParaView. View, I need the pipeline browser, which I need to integrate here so that you can see what happens. There, I have a data set. Actually, I have points here which are pretty small to see. There's something special. There's a special representation mode with point called Gaussian point. You see what Gaussian points are? If I do something else, for example, the point source, and I get 1,000,000 points here on my screen, or 100,000, we'll see what Gaussian point does for you. Okay, lots of points. By default, let me turn that off for a second. By default, those points are single dots on the screen. All right, but there is this Gaussian display mode, like this, which makes a really nice little spheres. The advantage of this, there's no polygonal representation. It's very lightweight because this is generated directly on the GPU. The GPU actually, what it shows you on the screen is not the image, it's not the projection of a little geometric object on the screen. It's an image, so it's a disk. It's an image of a disk, a very small image that is sized appropriately and put out on the screen. So that's why it's very light. You've seen that I've done 10,000 and I can do easily 1,000,000. I hope so, yes. And see, I can still move through 1,000,000 points here, no problem. So those are the point Gaussian. So to go back to my example here, I switched to point Gaussian because I wanted to see those points a little bit bigger. And I can act on the radius here of those point Gaussian, making them 3, for example. Now, see that effect? This is exactly because I have images of a sphere instead of a real sphere. So when one of them comes in front of the other, it flips out. So of course, don't exaggerate on the radius. This would be just a little bit too much. If I said 2, you would never know that there are images instead of real geometry. All right, that's my data set. And if I animate that data set, I have I lose them here over the screen, but here they are at time step 99. And if I go back to 0, yeah, I really need to, okay, this would be time 0. And here they animate, I made this up. This is a demonstration thing. Properties. What I want to show you is the source code. I have to get another window, otherwise it doesn't show on my screen. What is it called? Transient pi. There we go. Number of nodes 10, it's the number of points. I give them something we haven't seen yet, the VTK ID type. This is something specific to represent the ID in SPH, for example, particle IDs, so that we can track particles as they move from one processor to the other. We have here a command called set global IDs. So those would be IDs that are unique and global over a partitioned set of particles on a parallel server. And in my metadata information, I have a set of time steps here. So I've decided on making up 100 time steps. So the time step is an array, a Python array, I times 0.5 for 100 time steps. You have to define the range of time step, so that would be the first and the last time step in the array. You tell your pipeline the time range with that specific key and the number of time steps right here. With this, as you load this into ParaView, remember that the viewer drives the time. So what does the viewer do? The viewer reads this information. The viewer knows that there are 100 time steps available, and it knows their value. And it sends back to the pipeline the value of the time step it wants. And that value is read right here as this special key, update time step. In previous examples this morning, we've seen update extends. This was the thing, the dimensions of the grid we wanted to, the pipeline was asking us to generate. In this case, we are specifying a time step value. Based on that time step value, I do a little bit of a arithmetic here with the sinus and the name of time steps to generate data. And that's basically all. And then I set my output time step, data time step, to be exactly the value I have received as input. So this is how ParaView manages the fact that at this point in time here, if I put myself at 50, and if I look at my Python shell, get rendezvous dot view time, I have the value 25, which I think works out. I had time steps of 0.5 times 50 time step. We are at time step value 25. If I set that to be 30, and if I render, we should go up a little bit. There we go. So those are the time steps as seen by the pipeline. Now, if I find, I think I'm going to find one more example, which would be probably the best to demonstrate time step. I'm not sure to find it here, actually. Yes, it is. Okay, cool. ParaView. I will load this data set, which is part of the standard distribution of ParaView. I'll load it, and in the information tab of this particular data set, I finally have what I wanted to demonstrate, the list of time steps and their values. Okay. This is basically a can of, you know those drinks, I can't say the word, soda drinks. So it's half a can, and as I animate this, we crush this aluminum can. So here's the data set. Let's look at the Python object. This reader equals get active source. Has already there an object called time step values. And if I print it to the screen, I've got my, what are they, 43 time steps. So this is a Python array with 43 values of time step. What is missing in a lot of documentation, I've rarely seen that, in any case in the trace, would be how to animate the thing I just did here, playing the play button, doing this play. Okay, cool. How do you do this in Python? Well, we've seen that this Python object called reader has an array called time step value. We know now that the rendering window has the decision to update based on its view time. So it's 3 lines of Python code. For I in reader dot time step value, for I in range of view time equals that index, that array indexed by I render, and it automatically animates. Okay, I have those 3 lines of Python code written somewhere in a slide, but I forgot exactly where. In that particular case, the comparative view inspector still. Why is it not? Oh, I know what I'm doing. What I forgot to do is to go to the render view comparative here, and there. Whoops. Go to my comparative view inspector based on my can. I forgot how to use this. I forgot how to use it because I hardly ever use it. Why so? It's because it loads all the time step in memory. I hardly ever do that. But this is kind of a quick demonstration of you can view multiple time steps at the same time in ParaView with this so-called comparative view window. It basically by default sets here 4 quadrants where the views are independent, and you have the possibility to update those views based on different time steps. In this case, here you have multiple pipelines with the view where the view time is disconnected from each of those different windows. the synchronization of time step. In the filters, you have a special category called temporal here, where you can annotate, okay, the time filter, group time steps together, and you have this synchronized time. Perhaps this is something you were looking for, Tarun, here. Data to pass, data to synchronize. If we go to the help, remember that there's always the question mark on each of those filters button in ParaView. Somebody was asking about the documentation. You have here the documentation as provided by the class hierarchy on what the time, on what the particular module does. There are times where you are looking together at two different simulations that have different time steps and different outputs. And we have a filter here called snap to time step, I believe, where you can actually, for example, take one time step animation of a given data set, animate through those fixed time steps, and use the value of those time steps to interpolate into the second data set series, even if it has completely different time step and time step values. So it will do a linear interpolation between the two closest time steps to match the first series of data set. It's a bit complicated to demonstrate here, but that's how it works. I will do, okay, we're doing fine with the time, so let's do it here. Absolutely, to finish up on the molecule stuff, absolute brand new. This is dated 2 days ago. There was a commit in VTK, and it will show up in ParaView very soon. This simple bond perceiver module, which I have made you aware of, now comes with a P prefix here, which is it's a sign that it's implemented in parallel. This is going to be very interesting, very exciting for people doing, for example, LAMPs, GROMACs with very large atoms number. I'm talking here about hundreds of millions of atoms, etc., where we're going to do distributed visualization. We're going to split the molecule among the atoms, among multiple ParaView servers. And just like in the case of gridded data, where we need ghost cells to do a computation of gradients, for example, for the computation of bonds between atoms, we need to know at the border between two processors which atoms are close to, which atoms on the other processors are close to the atoms on my processor, so I can bond them together. So this is exactly what this is done. And I suppose, I don't know if it's going to make it for the 5.5 release, but in any case, if you want to use this at CSCS, we'll have it ready in the development, in the master version of ParaView, which I have on Piz Daint, tracking exactly the improvements in ParaView on a daily basis. So if that's your requirement, then you talk with me and I'll give you the special module which I make available. So in that case, instead of talking about ghost cells, we talk about ghost atoms, okay? And we'll have it in action here on Piz Daint very quickly. This related filter called distributed point cloud filter is part of a collection of algorithms that is made for point sets. They're called point sets in VTK, especially for SPH. We've talked a little bit about SPH during the lunch break, and I can demonstrate that now with ParaView. I'm going to make a million of atoms here on my screen just for the demonstration purpose. A million or less, it doesn't really. Where are my points? They're nowhere to be seen. All right, here's the standard data set, SPH. How do you interpolate through a data set that doesn't have connectivity? There's a special category here of point interpolators, which is taking me by surprise because it's not enabled. This is pretty strange. Point. Pardon me? Yeah, perhaps. Yeah, good point. So I'm going. Yeah, there is no data attached to those points. So thank you for the tip. I'm going to make some data. There's something called random attributes. I'll just use random attributes. And I'll say generate point scalars. Don't do this. And we're good with that. There we go. Thank you. You saved my life. Well, you saved my afternoon. This is very clever, actually. It shows you that the GUI knows when a possible connection can be made in the pipeline. It doesn't let you do stupid things. You can only connect things that match in terms of data types, data in mesh types, etc. So this is how, as you can see, this is specific to SPH because it's already asking here for a density array, a mass array, and a cutoff array. So the cutoff really relates to the SPH terminology of the SPH kernel. In this case, we're going to say none because this is not really SPH data. And we're going to have this as the result. What's happening, it's all 0, which means that the influence of each of those points was set to be something too small. So I'm going to raise this. This is the default argument here called a special step. I forgot what's a good value here for this data set. There, that I probably overdid it because now it's really computing a lot. And it's a good occasion to, it's done, to show you that if I set this to be 0.3, this is the load on my CPU here. All threads are active. Okay, now it's done. But you can see this peak of activity on the CPU. So all those SPH filters are implemented using, in this particular case, TBB. In ParaView, you can have multiple acceleration infrastructure. OpenMP, which I've tried, it's not quite as fast as TBB. TBB, the Intel threading blocks, which I use which I use a lot for SPH data. It works really well in this case. And soon there is some support with CUDA for the moment. I haven't had good results yet, so I don't really speak of it so much, but this will come. This, by the way, there is my plane. Okay, and those are my points here. So what have we done? We have interpolated, based on an SPH kernel, we have interpolated those points back onto a plane. This morning we had the question, can we do volume rendering of SPH data, of particle data? This would be the case. You would implement a box, an interpolation box around your points. In terms of acceleration, so TBB is a good option today. Soon, here also I have hesitated to discuss it at length during the tutorial. There will be VTKM. VTKM is the next phase of VTK. VTK now is old. It's 20 years of development. It has reached a point where new acceleration devices are available, acceleration libraries are available. VTKM is something that will be greatly accelerated directly with CUDA, things such as CUDA, for example, on the GPU. And this, I suppose, would be very, very much more mature in a year's time or so to show that in ParaView. The particular example here of the SPH accelerated with TBB has one limitation. You cannot mix and match MPI and TBB. This is the algorithm itself. It's not a limitation of ParaView. Recently, there is a module that has been contributed to ParaView called Solid Physics, the Solid Physics plugin, which enables both MPI, distributed computation on multiple servers, and TBB accelerated on the node. Okay, so this is something that is, solid physics is basically the type of simulations where you have multi-material components in your data volume, and it enables you to extract materials and things like this. And this is implemented, I've tested it with the examples given in ParaView. This is implemented as such in this mixed parallelism method, so it's really quite powerful. That's with this. So if we want to try the connection to ParaView, I think this is probably a good time now. I want to go back to the presentations that had the details, so you have them on the screen. That's the one. So are there Windows users here? 2. Oh, what a strange idea. No, it's, you need to go through this documentation here. So you need to build up the connection. And I want to show you something to debug your remote connection that is extremely useful, and it's valid both for Linux and for all types of users. Linux, Windows, and so forth. I will do it here. I will connect to Daint. I will again here summarize the example. The connection creates an SSH tunnel to the logging node, and then the compute node connects back to the logging node, thinking that it's its local client, and then the tunnel forwards the connection to your desktop. And it uses the port ID that you give it as the socket port. And this is what shows up in the graphical user interface here. You select the Piz server port, and here I use my ID, which is 1100. And the absolute best way to debug the connection to Piz Daint is the following. So here, if I use 1100, which is my ID, I'll show you what's happening. I'll go to Daint. If I do a net start minus NA, and I grab for that port ID, there we go. This is the tunnel. The tunnel has been established. It's listening on port 1100. So once you have that on Daint, you've gone through 99% of the hurdle of making that connection. Most of the problems I have with users which are just starting there and now we're connected, which people who are doing their initial configuration with ParaView, their problem with SSH. It's never a problem of ParaView. It's always SSH, SSH keys, etc. So you need to set up your keys correctly. This is why I insist, especially for Windows people, because sometimes the menu doesn't really pop up on your screen and you wait forever. And it's asking you to say, yes, connect to this. So create an SSH key, copy it to your authorized, what is the keyword? Authorized key in your .ssh directory. And from there, build up the tunnel and check with the command net start that your ID, there is a listening connection on that particular ID. So there I am connected. I'll stop this, exit. I'll go back to my presentation. So the setup. Let me first finish up with the Linux people who have less of a setup to do. Copy this workshop servers.pvsc from Daint into your local desktop, edit it, change the student star with your real username. That file can be stored anywhere. All you need to do is edit it with your username and then import it into ParaView. That file makes reference to the shell script which we use on Piz Daint. That file you copy and you leave it on Piz Daint, okay, because this is the shell script executed on the server side. You make a copy of it, it's much easier. Copy it to your home, for example. There you edit it and you can customize, put anything, any particular parameters you want for Slum. Specify your personal user ID here as the PV server port, And then this will be the number you check for in that netstat test. Okay? On the console, this is the output that you should see. Even if there are further problems with SSH key, this is the minimum you should see appear, and maybe it blocks at this time asking you for a password confirmation. So that's the S1 command, the number of tasks you've given, the logging name, and then your port number. For the Windows user, you first set up a session with Putty, call it reverse connect Daint, set up your username, set up that connection proxy with the command plink, and if it's easier, I can email you this directly to read and put in. Yeah, exactly. I have it ready or to be mailed already.
Are these slides available somewhere?
Yes, they are.
Yeah, it would be nice to send it per email.
They are. I'm going to send them to you immediately because.
Sorry, a question?
Yes,
Who has the page with the logins?
I do. It came back to my desk here. I don't know who.
Did the pencil also come there?
Pardon me?
Did the pencil come also?
No. You all use your own.
I gave mine.
Okay. On Piz Daint, the command ID is the one that prints your user ID. So the username shows up here in your Putty connection proxy here, one place, a second place here in this username menu, a third place in the command plink at Ella, and I think that's it. So 3 places you need to change the username. The address of the shell script here, rc submit pvserver.sh, you copy it to your home such that you can customize it later. Now, that address, home/rc submit, will become the new field which you see right here, okay? Here you have the remote script which generates the slum job. This will be your own address, user/stud, whatever number it is, /rc.
How to make the script executable in order to connect?
The script is executable, no?
Maybe because I did
Do you want to copy it with the CP?
No, you copy change the permission.
Change mode is the command, no? Change mode plus X. Change mode plus X.
Before I got the permission denied when that.
Change mode plus X and then the name of the file. I'm going to show you a web page on the official website of CSCS, right here on the user cscs.ch pages. Under scientific computing, you have the supported application, you have a ParaView page, and that basically summarizes the same things. It has one little addendum, which, if I can zoom in on the page, it doesn't let me zoom in. There we go. if you cannot, from your terminal, you should check that you can SSH to Daint directly. Depending on the Wi-Fi connection you've picked up, or if you're at ETH Zurich, perhaps you can already. In any case, you need to be able to access to Daint via the ELA gateway. So those 4 lines of code to add in your .ssh/config, that would do exactly the trick. And in that case, you can SSH directly given the Daint logging node. Just make sure to replace username here, of course, with your real username. Here, for any host, Daint star, so it would be valid for any logging nodes, .chch. We use the proxy command to forward the connection to the ELA cscs.ch gateway. All right, we've got most people working. Alexandra, how is it
Does
going?
that need a different SSH authentication than the normal connect to Daint? Because, so usually I connect just...
You could just, since you're going to be using that
So I
later.
just connect like this.
No,
Usually.
you need, no. Yeah, you really need the, exactly as in the instructions, you really
That's
need
what I was trying now.
Daint,
Yeah.
okay,
Yeah.
101, exactly.
And then so what I'm doing is I'm tunneling through
Yeah,
ELA,
yes.
which I'm usually doing as well.
Oh, okay.
And then I try to put this proxy
Okay,
information in.
okay, good.
But then it seems that I get an SSH program, because if I now try to connect like this, and then it closes, and then it tells me that I cannot connect to localhost.
This is probably a key. There's probably in your cache, in your SSH cache, something about the connection that needs to be removed.
And I need the proxy, right? If the normal Daint
Yes.
won't be enough,
Yes, exactly. You do.
because the normal Daint works just fine. It's just so I can log into my account,
Yeah.
just without the proxy thing. Here I just
Oh, I
tunnel.
see. But yeah. So what is? So this interface is
Is
slightly Is it a little bit different?
It
now?
looks a little bit different than the normal Putty, but it basically the only thing it does is opens Putty in front of the file manager.
Yeah, so let me check a little bit more. So you're not using the course ID, you're using your own ID.
I tried. I mean,
Yeah, I
it
mean,
should be both working, right?
it should, yeah, and it's probably we save time doing that. Proxy time. Why doesn't? I don't know what to.
And then I clicked on local, like you did in one of the slides, basically.
Oh, is it?
Yeah, and then you get the line, but like this.
Oh, okay.
let's say,
Oh, okay. Local proxy
You just
command.
go 1 second. You just go out of this into the test thing, so that I don't kill my. So here again. So I put in.
Okay,
the
okay. Yes, that is good. Yes, that is good. So what is the last part missing? Authentication. No, key exchange. SSH, no, S.
So why does it need a different SSH for this special proxy tunneling? Because it should recognize me as Daint user, right?
Oh, I know what's missing is the tunnel. Did you? Oh, the tunnel is here. Oh, sorry. Ah.
Oh, yeah, you see the
On my personal port here, or
Ah. here you need to set up, that's why it needs to be different. It needs a dedicated tunnel with your ID.
So here it needs my personal port?
No.
No.
It needs, I sent the instruction here by, so did you get
The email one?
the email I sent 20 minutes ago?
Yeah. Oops.
Let's look at it and I'll show you.
Yeah, but this I have open, right? Yeah, this one.
Okay,
Yeah.
so the page that matters is this. You need a reverse tunnel with your ID. So here in my case it's 1100, this would be your ID.
Yeah, whatever, yeah.
So you need this remote tunnel to localhost. This is what you need to set up. Otherwise
Instead of the ELA one.
ParaView will not work. That's exactly what you need.
So I need to set up
So-
instead of the ELA
So
thing?
yeah,
No, I still need to through tunnel through ELA, right?
yes you do actually. So I don't know in this user interface here, can you not bring up the regular Putty?
Yeah, I can just do it too.
Because I would find it,
So here I retried as well.
oh okay, okay, good, okay. So load it,
so
yeah.
this is what I did.
Okay, good.
And then here on the tunnel I put in, as you said, this is my
Yes,
personal thing.
okay, very good, reverse.
And wait, here?
No, that's
that's
done now, yeah.
So and then here on
On the
proxy,
proxy,
I put in this. with my
okay,
password and
that looks
username.
good.
And then here click local. Yeah, and that's all I needed for this, right?
Proxy host name.
So here I basically did exactly what it says. This
Yeah,
I did,
okay, okay.
this I did, I put my password, I put
Okay.
this, and I put auto login.
All right, so go back to your Putty.
Back.
Once you're here, can you save it?
Yeah, it's
Yeah.
saved.
Can you open it now?
Yeah, but then I get a black window.
Okay, so this is the test for you to do. Until you cannot directly open the connection to Daint 101, ParaView will never work anyway. So this has to be this has to function first.
Yeah.
And it's only a matter of SSH keys at this
Yeah,
point.
that's right.
Not even the tunnel. The tunnel doesn't really matter at this point. At this point, it's simply a matter of password.
So something in here needs to.
Yeah. So can you look a little bit for this? It's really a password problem here. As you know, there are a million tricks to be aware of. I'm going to show you one more little trick to save your life, to save a number of button clicks. When I connect to Daint here, let's give it a few seconds. You have to actively load the plugins, for example, the NVIDIA Index plugin. And in order to not have to redo this every time you log in, you can tell ParaView to automatically load on every time you connect. I'm going to show you the menu to do exactly this. Basically, that menu is under Manage Plugins. Let me give you an example here. For example, if I open up the PV NVIDIA Index plugin menu, I have here a box called Auto Load, and it's checked in. If you turn this on, you quit, the next time around it will automatically do it. So for those plugins you're going to load every time, that's the thing to do. So some of you have managed to connect to Daint. This is a great accomplishment, actually. You can feel proud. But first, so quit that for the moment. I would like you to exercise the NVIDIA plugin locally first, because it's really very powerful, and you'll already get quite a bit of experience playing with that. Once you do it locally and you've learned how to do it, then we can also do it on Daint, okay? But please exercise that already locally. Eduardo, help me out here. Of course, in client-server mode, the GPU on Piz Daint does the work and uses the index plugin, but you still have to load the plugin on the client side, right? Even so, for people who don't have an NVIDIA GPU on their desktop, they still cannot use the client-server connection, right? Because the GUI, they need the GUI. That's basically it. The problem is that.
We never tried that. I may try that.
Yeah.
A client without GPU.
Because you all understand that the client-server concept is that it's only the image being sent from the server back to your client. So for this, in fact, you shouldn't need to have an NVIDIA GPU. However, the plugin requires the GUI controls. And for those GUI controls to be active, you need to load the plugin. So I'm not sure if you can load the plugin anyway. It's worth trying, actually, because perhaps loading the plugin itself does not actually activate the GPU.
We fixed a bug recently because loading the index library was checking for exactly who has some dependencies on the CUDA driver. We don't have it. The machine was crashing. I think it's not in this version.
Yeah, okay.
So we need the NVIDIA GPU for today.
No, you need an NVIDIA GPU only if you want to exercise the NVIDIA plugin, but we showed a lot of other things that you can do with the regular stuff, okay?
Actually, the plugin loads, but when you try to do the filtering, it throws some errors.
Yeah, okay. Everybody, I'm going to answer a question from one student here. How do you make the geometry? This is the case of climate and atmospheric and geophysics. How do you make the surface to follow the altitude of your geometry? Well, for all those people doing geophysics-based visualization, first of all, I have here an example of there exists a file of the political boundaries and the land boundaries of the world. So I have it here displayed as, let's see, region of the world. And this is public domain data. So let me just orient my map. So we have South America here. Please trust me, it's upside down. It's flipped around. This is something I was working on yesterday evening, and it's just a matter of flipping the indices, but it's there. It's just to demonstrate that this file is called political borders.vtp. It's a VTK polydata file, which you are free to find on the net. If you don't find it, ask me for a copy of it. This will be the first thing to superimpose the land boundaries onto your surfaces. But then the real question is, how do you map, how do you elevate a surface based on a scale field? So I'll delete this. I'll get a standard plane of data. I'm going to do a cut plane here through this just to use as the example. So here I have a 2D data set in 3D space with a scale field. Can I basically make the red part in the middle go high as if it was a mountain? So let's assume this is the altitude. It's very simple. Go to filters. and get the filter called warp by scalars. If you warp that by scalars, here's the solution, but wait, there is something I have to change. Oh, use normals. This should be, this is the standard, so it should be 1, 0, 0. Let's see, there we go. So there we now have our nice little display. Let me put the slides back in. We see here the plane and then the mountains elevated. Let's make it a little bit less high. I'll set that to 0.3. Well, okay, something like this. And by the way, ParaView has some nice axes which you can put in there for your pictures to look a little bit more professional. Is that helping?
Yes, but the wrap doesn't work for my data.
Okay, so the wrap doesn't work for your data. What could be the reasons? You've seen here that the warp uses a normal vector to be, it has to be available. If your geometry, I've seen your geometry, if your geometry does not have a vector called normals, you can generate one. So there is a filter called generate surface normal. This is something you should insert into your pipeline before the warp. And I would generate a normal for each individual triangles in your surface. And then things should be okay. Now there are cases like you've seen in my previous pictures of the Earth where South America was just flipped like this. It's just because the surface had normals pointing inside towards the center of the Earth instead of normals pointing outside. And it's basically because, let's take my plane here. In the case of the cylinder, I can take this flat piece of paper, wrap it like this, or I can wrap it like that. And in that case, the inside here of my cylinder, the inside becomes the outside if I flip it like this. So it can be as simple as this. Oftentimes, so that problem I will fix with my boundaries is just to warp. And in the generate surface normal filters, there's a button to click, flip normals. It would do exactly that. So you try one or the other until it works.
But I cannot generate the normals here.
You cannot. Okay, that's a good. That's very good because we're working in an interactive fashion. So the generate surface normal is not available. The answer is probably because your data is not of type VTK polydata. How do you get a VTK polydata? You insert on top of it the filter called extract surface, and that will convert your presumably VTK structured grid into a VTK polydata type. At that point, the generate surface normal is enabled. You make the normals, and then you warp it. Try it out, and if it doesn't work, pardon me?
I cannot extract surface.
Okay.
I basically cannot do anything there with the data. I don't know why.
All right, I think it's time for coffee. In fact, it's a good time for coffee. So if you are more or less done, you are welcome to stop now for a cup of coffee. I will come to your desk to make those normals work, okay? And then we'll come to coffee right afterwards. So let's take a break.